Hello, am I audible?
Good evening, ma'am. You are audible, ma'am.
Yeah, very good evening. Is there something lag or echo in my voice?
Yes, ma'am. There is echo in your voice.
Okay, just give me a second. Hello, am I audible now?
Yes,
Yes,
ma'am.
yes.
You
Ma'am,
Okay,
you're audible.
Yes, ma'am.
okay. So let's start. So today is our first revision session. So we are starting from the last week. So that means first we will cover week 9 to 11, and then uh, in the next revision sessions we will cover from week 5 to 4 and then go on in this way. Okay. So today we will cover all the I have selected some of the important topics because you know that the content in week 10 and week 11 is very huge, so we cannot cover all things in a lecture. So but I have selected the important topics, so whatever important uh, in the mean of end term exam, so you can go with these topics at least. So these are your at least requirements, so that means you need to focus on these topics at least. Okay, so let me share my screen. Okay, so today is our revision session for week 9 to 11. So these are the topics I have selected. So first we'll go with what are local maxima and local minima for a function. So that means how we can find out the local maxima, local minima. So we know that for that we need to uh, use the help of second derivative test, right? So after that we'll go to how to find the area under the curve. So here I have skipped the process of Riemann integration because the Riemann integration is a huge process, and we know that it's not possible to solve any question if it is based on Riemann integration within 10 to 15 minutes, right? So from the exam perspective, Riemann integration is not that important topics. I'll skip the Riemann integration and we'll just understand what are the application of integration. So that means how can we compute the area under the curve. After that, I'll go to fundamental theorem of calculus, which somewhat relate antiderivative topic to with the Riemann integration or indefinite integration, right? It's a very small results which says that integration a to b f of x dx is equals to capital F of b minus capital F of a. Where this, what is this capital F? It's a antiderivative of small f function. So that means if you find the derivative of capital F, you will get small f back. Okay, so we'll cover what is fundamental theorem of calculus, and then we'll move to graph theory part. So these all graph theory part. So start with what is a vertex cover, what is independent set, graph coloring, and then BFS, DFS processes, as well as what is a tree. We know that tree is nothing but a special type of graph with two basic properties. First of all, it's acyclic, and second of all, it is connected, right? So connected acyclic graph is a tree. So I'll cover that too. And then we'll go to the topic of minimal cost spanning tree. Okay, so here we have, so that means in graph theory, we generally have four algorithms. One is our Descartes algorithm. Okay, and second is our Bellman-Ford algorithm. Then we have Floyd-Warshall algorithm. And then we have Prim's algorithm and Kushkal's algorithm. So that means we have mainly five algorithms. Okay, Kushkal's algorithm, right? So we know that for finding something or for finding minimal cost or a shortest path using Bellman-Ford and Floyd-Warshall algorithm takes a lot of time, right? So that means these algorithms are somewhat lengthier to apply, or it will take much and more time to apply these algorithms. So that's why they are not that important. But it's good to have to. It's actually necessary. You should know in which cases we are using these algorithms. Okay, so I'll discuss these three algorithms in very short time, and I'll cover what are the theoretical aspect of these algorithms. So that means what are the requirements we need to apply these algorithms. Okay, and after that I'll cover in details Prim's and Kushkal's algorithm, which are very easy and which we'll use to find out minimal cost spanning tree. Okay, so for that I have selected some of the examples. We'll do those examples too. So my idea is to start with the topic and then go with the examples. Okay. So in meanwhile, if you guys have any doubts or anything, either you can raise your hands or you can unmute yourself and ask me. Okay. So I'll take a pause between each and every topic. Then we can discuss whatever doubts you guys have. Okay. And at the end, we can solve some of your doubts or some of PYQs, whatever things we have left. Okay. So let's start with local maxima and local minima. What is a local max and local minima of a function? In meantime, if there is some issue from my side, just let me know. Okay. So, what is the local maxima and local minima? So, suppose if you have a function like this, suppose this is your function, then there are some points which possess some important properties. For example, here, if you consider this point, suppose this is some x is equals to -5. Now, what is happening around this point? If you create a small neighborhood and if you find out the function values over these small neighborhoods, that means all function values taken over this particular small neighborhood around the point x is equals to -5. Now, what is happening here? Here, the value of the function taken at f is equals to x is equals to -5 is actually less than all values taken by the function in this particular small interval, right? Where you can say that x naught is a part of a very small interval, whatever this interval is. Okay, so here we are getting that there is a small interval around the point x is equals to -5 on which the value of function is lesser than every other values, right? So such points are known to be the point of local minima. So these are the point of local minima. Okay. Similarly, we can
The
describe what are the
f of x should be lesser.
yeah,
Around
f of x should be lesser.
lesser.
Yeah. Okay, that's why minima. Okay, minimum value. Now, similarly, we can take some maximum points also. So, for example, here only we can consider this point. So here at this point, suppose x is equals to 0 is the
It should be lesser. Matlab, see, for example, if it is point is -20,
yeah.
around it will be -18 or -17. So numerically, it is not lesser.
Yeah, numerically it's not lesser, but we are treating functions value, not x
Yeah,
value.
function
Whatever
value only,
value
madam.
function. Yeah,
If minima
function
is
value.
-20,
Hmm.
y-axis, it is that point is at -20. Around that
Yeah.
point, it will be above -20, no? Like it will be more than -20.
Yeah, function value should be more than -20, but you have to take excess from here, right? So what you are saying, function value is lesser. This
Okay.
f of -5 is lesser, so x is equals to -5 is the point of local minimum.
Okay.
Right?
Thank you, ma'am. Sorry.
Now, if we take it is -5 from left hand side, if you take it would be minus 6.999 like that, right?
Yeah, it's okay, it's okay. We need a small interval. It doesn't matter how what is the
Okay.
length. We need at least very small interval.
No,
It's
for
okay
if
if
it
you
is
take
okay.
yeah.
If you take
That's it.
6.99, for example, the function value would be higher than f of -5, right?
Yeah.
And for if you take 5.99, then it would be lesser,
Higher
no?
than no,
No,
still
no,
higher.
higher.
We need this inequality to possess over this particular interval. Right? F of -5 should be less than equal to f of x naught.
Oh,
Okay.
on both the
At this
sides.
point. On both the sides.
Oh.
Not on a particular side. So we are not talking about increasing, decreasing function, right? So it's a function which is where the value of function at -5 is lesser than every other value of the function. Okay. Similarly, we can understand this by local maxima also. So here what is happening? The value f of 0 is greater than or equal to all other values f of x naught. And suppose this is very small interval where x naught is a part of a small interval around 0.0. Okay, so here this x is equals to 0 is the point of local maximum. Okay, so that's why this word local is important. Local means we need very small interval, very small. This type of small interval around the point. And if this property possesses over that small interval, it's our local maxima or local minimum. Okay. But
If
for
it is
global,
for
yeah.
example, I'll tell you, if it is less than that around 1, if it is
Mhm.
minus 1, then f of
Mhm.
minus 1 should be less than f of 0. You mean that?
Yeah. But
And if you take,
you
and if
can take very close interval. So for example, it's not
okay,
true
that
for
is close
-1.
interval. Okay, that
Yeah.
is close interval, I understand. For example, only I'm telling you. If it is
Yeah.
positive 1 plus 1, even then
Yeah.
that f of 0 should be greater than f of plus 1.
Correct.
But that is okay.
Yeah. Okay, fine. So that's why local means you need at least some very small interval around that point. It's not necessary to be length of 1 or length of 0.5. You can take very small 0.000 something, right? That's all enough for considering a local maxima or local minimum. Okay. So there is one another term which is global maxima or global minima. So what we'll do, we'll consider all values of function. Okay. So among all values of function, if there is a point, so these are all local maxima and local minima. What is a global maxima or global minima? Is this thing. So suppose you have a function f from some domain to some other range, right? So whatever the domain codomain you have, and if the value of f of x naught is greater than equal to f of x for all x belongs to the. So here what is happening? You have to compare the value of function to all other values of function, not a small interval, all other values of function. Okay, so such point x naught is known to be global maximum. Okay, because it's a global thing, right? You have to consider all other points, all other values of function over all the domain, right? So this point is known to be global maximum. And similarly, we can define global minima. So for global minima, the value of function f of x1 should be less than equal to f of x for all x belongs to our domain. Okay, so here this point x1 will be our global minima.
Ma'am,
Okay.
small question, small query.
Yes.
Suppose after doing first derivative, we'll be getting equation for we'll be getting roots for the equation, right? So
Yeah.
if we keep on substituting in the main function, wherever
Mhm.
the highest number is coming, for which value the highest number it gives, that will be
Mhm.
the global
No,
maximum or
no, no, no,
minimum.
no, no, no. That's not how we have to calculate. Actually, what happens if you have a function from real number to real number, you have to find out all local maxima and all local minima. And among them, whatever higher value is there, that value you can choose as a local global maxima. Okay. So these derivative things, so the higher value at derivative is not the case. We will use second derivative test. Okay. So you have whatever you have saying, it's partially correct, but not exactly. So there is one second derivative test.
Okay. Here, if we substitute those roots in second derivative, if it is less than, that means it is
Correct.
local maxima.
Yeah, that's what you have to do. So in second derivative test, what you have to do, first of all, find all points where the first derivative is vanishing. That means f dash of x is equals to 0. So what you have to do, first you have to solve this equation and you have to get several roots. Okay. So suppose you have some roots. Suppose you have some root x1, x0, and so suppose x0 is a point such that f of f dash at x0 is equals to 0. Then what you have to do, over these roots, you have to check the sign of second derivative. Here the first statement says, if the second derivative at this point is greater than 0, then you can say that at x is equals to x0, we have a local minima. Okay, so that means we have to substitute the roots of this equation into the second derivative. And then we have to check the sign. So if it's strictly greater than 0, it's a local minima. And if the sign of second derivative is strictly less than 0, then you can say that this is the local maxima. And if the value of second derivative is equal to 0, then we can say that our test here is failed. Such no conclusion.
And is this a
You can
saddle
wait.
point, ma'am?
Sorry, what?
The third condition is this saddle point.
Yeah, so we can consider it into saddle points, but actually the theory of saddle points is too vast. So for these points, okay, so we can call these points as a saddle point.
Okay.
Okay, it's not the exact meaning of saddle point, but for time being, you can consider. Okay, so saddle points are actually those critical points where function does not possess any maxima or minimum. So those points are saddle points. So from this one, we cannot actually conclude, but for our course, you can assume whatever points here you will get for which second derivative is vanishing, you can consider those points as a saddle point. Okay.
The
Yes,
question
sir.
is, if I answer, when I get f double dash x of 0 equal to 0, and yeah, the option says saddle point, no conclusion. So can I tick saddle point to get the mark?
Yeah, you can take.
Okay.
But such
So-
type of confusion won't be there. That thing we can
Okay,
show.
okay, no problem, madam. Thank you.
Okay. So there's one question in chat. Global maximum or minimum must have one value. So what does this mean actually? So it is possible to get, sorry, actually it is not possible to get global maxima and global minima over exact at one point, because if it is happening, then you are getting two outputs for a one input, which is not the definition of function. Okay. So this is the thing. And a function can have global maxima, it can have local maxima at several points. For example, if you consider a constant function, suppose you have a function f of x is equals to 1. Okay. Now it is happening here at every point of the domain, we are getting output to be equal to 1. So that means here 1. So that means all points are local maxima also, local minima also, and global maxima, global minima, right? So it is possible to get several local maximas, several local minimas, and several global maximas, several global minimas. Okay, you can take an example of a constant function itself. Okay, is this point clear? That means there is no uniqueness. We can have several local maxima, several local minimas, several global maxima, several global minimas too, because of the constant function only. Okay.
For this to be defined, like we need to mention the interval, right? The domain
Yeah,
in
we
which we
need
are
to.
looking. Otherwise,
That's correct.
that won't make sense, right?
Correct. But in general, if the domain is not given to you, you can consider that as a real number set, right? Set of real number as your domain. Okay. If it is not mentioned in any question, if the domain is not mentioned, you have to consider set of real number as the domain of function. Okay. Now, let's go to the next topic. So it's a very basic thing. What you have to do, it's a process. First of all, you have to solve this equation f dash of x is equals to 0. Find all possible roots, and then over all possible roots, you have to check the sign of f double dash at x. Okay, and then you have to judge whether it's a local maximum or local minimum. It's a straightforward topic, right? Is there any doubt so far?
But global maximum and minimum, the
Yeah. So for
concept.
finding global maxima, what you have to do, you have to consider all local maxima and find the max of that. So we have to find the max of all possible local maximas, right? So whatever local maximas are there, you have to choose the highest one. Okay.
Oh,
So this
okay,
is the
got it.
case. Yeah. And similar for minimum too. You have to
So
find out
basically
minimum of,
after first
yeah.
derivative, whatever roots are come,
Mhm.
all those values we need to substitute in the main function, right? And wherever
We have to substitute in the second derivative, not in the main function. In the second derivative. See, here we are substituting in the second derivative. And then you have to check the sign. Yeah, but
okay,
then you have to go for the function value for finding global maximum.
Not only roots, no, madam. The endpoints also we have to take, no?
Yeah, if it's a closed interval, then we have to consider endpoints. But if it's a function from real number to real name, then we don't have to. So what Naren was saying, if we have a function from closed interval a comma b, then we have to consider the points. So here, in this case, we have to check for global maxima is actually the max of all. So here the codomain could be anything. Okay. So here all the local maxima and these two endpoints also you have to consider. Because see at endpoints it's possible to it's possible that we cannot find f dash, right? Because at endpoint we know that there are several tangents, so derivative may not be defined at that point. So that's the thing we have to consider it. But see, we never want you guys to find out local max or local minimum. Okay. So it's kind of obvious if you are able to find out we never want you to find out global maxima or global minimum, right? Because if you if you are able to find local max, local minima, that's more than sufficient. Okay.
Okay, ma'am. Thank you.
But you know the process, right? You just have to consider the max value.
Yes.
Ma'am, why you removed me from the batch of statics?
I actually don't have any idea about you and the batch of stats. Actually, I'm the maths instructor, so I don't know about that course. You can ask the stat people, okay?
But
I
how I
actually
am
don't know.
joining again the class?
Yeah, so you have to mail to support team. That thing you
Okay.
can do. Okay,
Okay.
because I actually cannot help because it's another subject, so it's not in my range.
Okay. Thank you.
Now, the next topic is Riemann integration. But you guys know that finding integration using Riemann integration process, it's a huge part, right? We have to go for partitions, then go for limit, then have to apply limits and all those things. So I'll skip that part and I'll go to indefinite integration or area under the curve. Okay, so we know that if we have a function, if you have a very simple type of function, suppose this is your function f of x, and you want to find out this particular area, shaded area. Okay, so what you will do, we will say that we know that the area is nothing but, so here it's the limit is x is equals to 0, but we can take some other functions like this only. And suppose you want to find out the area under the with the boundaries x is equals to a, x is equals to b, and here this is our function f of x, and this area we need to find. So we know that by integration, area is nothing but integration a to b f of x dx. It's a simple result that area under the curve f of x is nothing but the integration from a to b f of x dx. Now it's a simple case. Now suppose in place of f of x, if we have more than one functions and we need to find out the area under the curve enclosed by these two functions. Okay, so for example, if you have such type of situation, okay, so suppose this upper one is your f of x function, this lower one is your g of x function, and you want to find out the area enclosed by the functions f of x and g of x within the boundary of x is equals to a and x is equals to b. Okay, so that means we need to find out this particular area. Then how can we do that? Okay, so for that we'll use the simple trick that what we'll do, we'll find the point C where these two functions are intersecting or cutting each other. So that is that this point x is equals to C. And what we'll do, we'll decompose this particular area into two parts. Right now it's easy to find out this area because this particular area, suppose this is your A1, and we know that A1 is nothing but integration a to b f of x dx minus integration a to b g of x dx. Right, that means this whole area, and then we are subtracting the area covered by the function g of x. Right, so we'll get our required area. So same thing we can apply for finding the area here too, a2.
Right.
Right.
A
Will
to
be
B.
A2?
Ma'am, A to B or A to C, ma'am? This one.
Oh,
A1.
sorry, it's a to c.
Okay.
We have to use the midpoint. So what will be the area of region A2? It will be similar, but in the reverse order, right? Because this upper function is g of x, lower function is f of x. So here the area E2 will be integration c to b. Now you have to consider this point. So integration c to b of g of x dx minus integration of same thing here also. Here also the point c will come. C to b f of x dx. Okay. So that's all about area. So we can find out area of any function, any curve, or an area under any curve, right? If it's a simpler one or it's something of intersection of two functions too. Okay. That's all about area. Is there any doubt from how to find the area under the curve? I think it's straightforward.
Hello.
Yes, Neetu.
Ma'am, I have a question to ask from graded assignment 9.
Okay. Is it related to area under the curve?
Yes, ma'am.
Yeah, you can paste it over the chat. I'll look and then we can discuss. Okay, just paste that question over the chat in the chat.
Madam, can you show me that again, madam? The difference between two curves. So what we are
Yes.
doing is f of x, we are finding out the area. So that will be one particular full area, and then you are subtracting g of x.
Yeah, correct.
Show me the graph, madam. Little bit,
Yeah.
little down. Yes.
Right. So this bigger area subtracting this area. Okay. So what you are doing? This is the whole bigger area.
F
And
of
then
x is
for
the
this
whole
area,
area.
yeah, and then we are subtracting the area covered by the function g of x, right? So we'll get our required area. So that's the
But this side, right side of x equal to c,
so
from bigger
here
you are subtracting smaller,
this is
no?
our this is our g of x function. So here
Yes,
the area covered by the function g of x is bigger. So that's why we are subtracting from g of x the area covered by the function f of x.
Okay, madam. But are we supposed to find out c also, where it is
Yeah, you have to
intersecting? Then only we have to do the difference.
correct. So
No,
first you
because
have to
with
find
the
out the
function,
point.
with the formula, whatever the function is, without graph, we'll not be able to understand which is bigger, which is smaller, no, madam. How to
Yeah,
go with
correct.
them?
So they
So,
will give you very simple functions. For example, you know straight lines, right? You know
okay,
parabolas, you know these.
okay,
These are very easy to draw.
okay,
Obviously, if
okay,
those type of functions will be there, right?
okay. So, freehand sketch, we have to draw and understand
Yeah,
the area. Okay.
right. That's
Madam,
correct.
one more, I have sent one message in the chat box. If
Mm.
it can be answered later, also no problem, madam.
Okay. Yeah, I was just reading that. Yeah, so for integration by parts, we generally consider there is one formula, some isolate or something, right? So that means first you have to consider for differentiation. Okay. So for differentiation, you have to take those functions which whose derivative is lesser. So for example, polynomials are there. So if you differentiate an n degree polynomial, you will get an n minus 1 degree polynomial back, right? Polynomials are there, or some log functions are there, which you have to consider for differentiation. Okay, so that formula you can recall, Ravi. I'm not remembering now, but there is some isolate type of formula that which function you have to consider
Yeah,
as a
I
first
have
function.
sent one more message.
Yeah, right. And for substitution, that thing depends on the integration. So you have to look for this form. That is integration A to B f of g of x into g dash of x dx. Okay. So you have to look for this particular form, and then you have to consider this g of x as your substitution. You have to take this to be equal to t. Okay. So our question is there. First of all, you have to find what is this g function. So for example, I'll take one simple example. Here you can guess. So suppose integration 0 to 1 and the 3x square plus 2 dx, right? And here I'm getting that x cube plus 2x, right? So in this question, which function you will consider as your substitution?
X cube plus 2x.
Correct, x cube plus 2x. Because here, if you take g of x as your x cube plus 2x, then what is g dash of x? G dash of x is simply 3x square plus 2, which is here. So that means here we have the form g dash of x dx. So you have to check for this form where you are getting g dash of x dx, and then we have gx here, but we can solve it. It's simply become the range will differ, right? So the range you can find out. It simply become dt upon some t here, right? Something like this only. So you have to first find out this type of thing, g dash of x dx. Is that okay?
Okay, madam. We'll see. We'll continue, madam.
Yeah. So that's all about
Ma'am,
calculus part.
Madam,
hello,
the-
Yeah.
hello, ma'am.
Yes. Thank you.
How can I share my document on chat
You can
box?
take screenshot and paste it over here in chat box.
Ma'am, I have taken the screenshot, but I'm not able to send it in the chat box.
See, there is one option file. So have you joined with your mobile phone?
Yes, ma'am.
Okay, so then you can let me know the question number at the end. We can discuss that at the end if it is okay for
Okay,
you.
ma'am. Okay,
Okay.
ma'am. Thank you, ma'am.
Just remind me once.
ma'am,
Okay,
if
yes.
that intersection point, the two functions are given, we need to first find the intersection point, right?
Right.
If it is algebraic two algebraic functions are there, you have to find the intersection point between those two and then find the C midpoint, where
Correct.
the two functions.
Right. you can find the intersection point just by equating two expressions, right?
Yeah.
So for finding, you have to just solve f of x minus g of x is equals to 0. By solving this equation, you can
Yeah,
find all the intersection points, right? Okay. So now let's move towards graph theory part. Okay.
Ma'am,
In
I
graph
have a
theory,
general doubt, please.
yes, Santosh.
How to calculate critical point?
Critical point, for calculating critical point. So what are critical points? So first you have to recall the definition. What is a critical point? Sorry. So critical points are these points are have two types of nature. So one thing, all those points or for which f dash of x is equals to 0, those points are known to be critical points, or f is not differentiable at those points. F is not differentiable at these points. So those points which possess one of these properties are known to be critical points. So either the derivative is equals to 0 or f is not differentiable at those points. Okay, so you need at least one of the property to say that that point x naught is a critical point. So you can find out just by looking at f dash of x naught is equals to 0 or those points where the function is not differentiable. That's your critical point. Is that okay, Santosh?
Yes, ma'am.
Just solve this equation f dash of x is equals to 0. Okay. So now let's go to graph theory part. So we know that first of all, what is a graph? So graph is nothing but a pair of two sets. One is the set of vertices, another one is a set of edges, right? So we have to combine these two things to form a graph. Now in graph, we have several definitions: vertex cover, independent set, matchings, graph coloring, and all those things. So I'll take three important topics, which is vertex cover, independent set, and graph coloring. So I'll start with what is a vertex cover. Okay. So here, as the name suggested, what you have to do, you have to find out all those vertices which can cover our graph, right? So you have to find out all those vertices which can cover our graph. So that means ultimately we are finding vertices, right? So what is a vertex cover? So vertex cover is that subset of set of vertices which can cover the graph. Okay, what is the meaning of covering a graph? Meaning of covering a graph means if you consider any edge from the graph, then at least one of the endpoint of the edge should belong to our set. Okay, so what is the meaning of covering the graph? Covering the graph. Covering the graph means for every edge, or for each edge, at least one endpoint of that edge should belong to the graph. For each edge, at least one endpoint should belong to the graph.
Hello, ma'am.
Yes.
Should belong to the subset, no, madam.
Subset, sorry. Yeah. So should belong to the subset. Yes, there's someone.
Ma'am, firstly, will you please cover the week 9 every point?
Sorry, but it's a revision session, right? So I cannot cover each and every part of week 9. I have selected some important topics. If you want to if you want to cover each and every topic, you can just go and see the previous sessions. Those are already uploaded over YouTube. You can just go and look there. Is that okay, Muskan?
Okay,
So
ma'am.
let's see some of the
Ma'am,
examples of vertex cover.
Yeah, exactly.
Yeah.
Sorry,
see-
ma'am. You were telling examples and I was asking for
Yeah.
this. Thank you.
Mhm.
Good.
So I'll start with a very simple example. So suppose this is your graph. Okay, very simple graph of 4 vertices. 1, 2, 3, 4. Right. So suppose I'll give them some name ABC. Right. So here, first of all, tell me what are the possible vertex cover are there. Okay, so one I'll tell you. So the first vertex cover, VC1 I'll say. So the first vertex cover is I can consider any of the 3 vertices, right? Suppose I'll take A, B, and C. So if you have taken A, B, and C as your vertex cover, Now what these vertices should do, they should cover the graph. Cover the graph means if there is an edge if there is an edge in your graph, then at least one endpoint of that particular edge should belong to our subset. Okay, so let's see what are the edges in our graph. So first is this edge, right? So what is the endpoint of this edge? The endpoints are D and C, and this C is belonging to our graph. So that means this vertex C is covering this edge, and this edge. So that means the C is taking care of three edges. Similarly, the other vertex is our vertex number B. So vertex number B is covering this particular edge, and this particular edge. And vertex A is covering this particular edge, and this edge. So if you combine all three vertices, then you can see that vertex A is taking care of these three edges, vertex B is taking care of these three edges, and vertex C is taking care of these three. So ultimately, all edges of the graph are covered. So this is the meaning of covering of a graph. So that means this particular subset of vertices can be treated as a vertex cover. So this is one vertex cover. What could be the another vertex cover? Can someone give me another vertex cover of this particular example?
ADC.
D and B.
Yeah. So one is ADC, obviously, but we can also create one vertex cover with lesser number of vertices, right? So here in these two examples, you can observe that we are using three vertices, but it is possible to create a vertex cover with less than three vertices, right? So we can take A and C, we can take B and D also. You can so this is VC1, VC2, VC3, VC4. We can take A and C we have taken, we can take B and D too.
But if you take AC, that
A and C,
BD
B.
will not be covered.
Yes. One edge will
AC
be
is
missing.
For AC, BD will not be covered.
BD edge will be missing.
yeah, that's correct. That's a good point. So if I'll take A and C, then this particular edge is missing. That's a good point. And similarly, if I take B and D also, then also this one diagonal is missing there, right? So this one,
Minimum
and,
3 are required.
right. So that means these two are not a part of vertex cover. Thank you. So these are not vertex cover. Because of two diagonals. If we have one diagonal, then two vertices can make a vertex cover, right? So here these are not a vertex cover. So that means we need at least three vertices to cover our graph, right? So here this number 3 is known to be the length of your minimum vertex cover. So or we can say that we need at least three vertices to form a vertex cover. Okay, so here you can observe that the minimum vertex cover can be different, but the number 3 is unique. So how many vertices do we need? How many minimum number of vertices do we need? Is the question is generally asked. So that means we need at least 3 vertices to cover this graph. Okay, so the length of minimum vertex cover will be 3, or the number of vertices we need to form a minimum vertex cover is 3. Okay, so this vertex cover is known to be minimum vertex cover. Why the minimum? Because we need minimum number of vertices. Okay. I'll take one more example about vertex cover.
Ma'am, if we consider this, if you find a tree for this graph, that means it's equal to the vertex cover, right? Because that gives
Not
the
in
minimum,
all cases.
which is n minus 1. This is n is 4. Tree
Yeah.
gives n minus 1 vertex
Yeah, but
number.
not in all cases.
Okay, so we cannot say that finding a tree of a graph, it is not equal to the vertex cover.
It's not equal to vertex cover. For example, if I remove one diagonal here, then only two vertices are enough to cover the graph, right? As
Okay.
you as
Sure.
we pointed
Okay.
out, right?
Fine.
So same thing you can. So let's take one more example. So suppose I have this vertex, this graph. This is 1, 2, 3, 4, 5, 6, 7. Okay. So here, what will be the length of minimal vertex cover, or how many vertices we need to form a minimal vertex cover?
1, right? 1. Center 1.
One. Correct. Only center one will be enough. Because this particular one will take care of all edges. It will cover all edges. Okay. Now what happens if I have some more edges here? So for example, I will connect these vertices too. Now in this case, what will be the minimum, what will be the length of minimum vertex cover? So let's figure it out, right? So ultimately, we actually don't have a closed formula. So that means we don't have formula on which if we substitute value, we'll get that. We have to go with our intuition, okay? So one thing is clear. So whenever you have to choose the vertex cover, you have to go for that vertex which has maximum degree, right? Because if for some vertex has maximum degree, that vertex will take care of maximum number of edges, right? So it's kind of obvious to take one in our vertex cover, right? Because if you take one in your vertex cover, one can take care of all these edges. And one obviously is of maximum degree. So what is the degree of one here? What is the degree of vertex 1?
6.
5,
6.
1, 2,
Ma'am,
3, 4, 5,
6.
6,
Edges are there.
6.
Right. Now all other vertices are of 2 degrees, so it's we now don't have any choices, so we can go with whatever vertex you need. So for example, I'll take 4. Yeah, alternate obviously.
vertices.
Right. So 4, then 2. So 2 will take care of these 2 edges, and then 6. 6 will take care of these 2 edges. So here the length of minimal vertex cover is nothing but 4. We need at least 4 vertices to form a minimal vertex cover. Okay. Is that clear? Any doubt so far? Okay, I'll take one more example and you
Can
guys
you
can
repeat
answer.
this again, ma'am? Last, can you
No,
repeat
in
this
this
again?
in this graph,
Yeah.
instead of taking 1, if I take 6 and 3, and then so 6 will
instead
cover
of taking
7.
1,
Yeah, I'm
that's
not taking
also covered.
1. I'm taking 6 and 3. So with the 6 of 3, everything will be covered. Any opposite 2.
6 and 3.
7, 4, 5, 2, 6, 3. Any
No,
opposite
but
2
these
will
2
be.
edges won't be covered.
Why? If I
If you take 6 and 3, let's
then
see. So suppose
6
6
will
and 3
cover
will take.
this one.
6 will cover
Yes.
these 3 edges.
They, right.
3 will cover these 3 edges, but these edges are not there, right? So many edges are not there. Let me draw this. This one, this one, this one, this one,
Right.
this one, this one, right? But there are other edges too. These edges are not covered, right? 4 or 5 edges are there, right?
Got it.
It's good to explore because here you just have to use your logic to find out vertex cover and independent set. We don't have a formula. So the one trick you can say, you have to consider that vertex which has maximum degree, or which consider maximum number of edges, right? That vertex can help us. Okay, now let's take one more example. So in this graph, let's see what you guys will think about this graph. So what will be the minimum vertex cover here?
2.
Okay, so
B
what are
and
these
E.
2 vertices?
B.
B and E. B and E.
A and
B and E.
E.
B and E.
B and E.
B and E.
Yes. So this B will take care of these 3 edges and E will take care of rest of 2 edges, right? So that's how we can compute what is the number of vertices we need to form a minimum vertex cover. Okay, is that clear? Any doubt in topic of vertex cover?
Ma'am,
ma'am.
if it is given with the adjacency matrix, so is it possible to?
Okay, just 1 second. Hello, I'm audible now.
Yes, ma'am.
So what was the doubt? Someone asked some doubt, no?
Yes, ma'am. If adjacency matrix is given, is it possible to know the vertex cover?
Yeah, it is possible, but you have to do, you have to create the graph using adjacency matrix and then go for vertex cover. Directly from adjacency matrix, it's a little tough to find a vertex cover. What you can do from adjacency matrix, you can create a graph easily, right? Just consider the vertices and whatever ones are there, put the edges. You can create a graph and then using the graph, you can find the vertex cover. Directly, it's a little tough. It is possible that you may miss some of the vertices. Right? Okay. Now let's go to the second topic, which is independent set. Okay, so before understanding independent set, what are the adjacent vertices? Okay, adjacent vertices are what? So adjacent vertices are those vertices which are connected by a direct edge. Okay, so if there is a direct edge between the vertex U and V, right? So direct edge means a direct edge. Then U and V are adjacent. Adjacent, or you can say as a neighbor or connected, directly connected. Okay, so what is an independent set? Again, we have to pick some vertices only. So what you have to do, you have to pick those vertices, vertices which are non-adjacent, non-adjacent, right? So that means you have to consider those vertices which are not directly connected with each other. Okay, so let's see some examples. So suppose I'll take the similar example. Suppose we have the same graph, this particular graph. Now, can you give me one independent set? What is the possible of one independent set? What vertices we can choose?
B.
D. But if you choose B, then
Oh, DB also not possible.
they,
Okay.
yeah, not possible. They are connected, right? So that means only one vertex we
One.
can choose here. Right?
Because D is connected to all other vertices.
Correct. So that means in this graph, it is possible to have several independent sets, but we need only one vertex. We cannot consider more than one vertex. Right?
But is it
So
not
here what?
necessary to cover all the edges?
No, in independent set, it's not necessary to cover all edges. Only thing you have to consider is those vertices should not be directly connected by an edge.
Madam,
Adjacent.
this will hold good for even for directed graphs?
Yeah, it's hold for directed graph, but in general, we don't define these concepts for directed graph. It's a little tough to go with outgoing edges and incoming
No,
edges, which
but
we'll
this
consider.
chemicals example that we have to find independent set only. No, madam, some chemical reacts with some other chemical.
Yeah, but that's not directed graph, right? You can put any chemical to any other chemical. They will always react, right?
Correct. Okay.
For my vertex cover, we have to find the minimum number of vertices. For independent set, we have to cover maximum vertices.
Maximum vertices. So that means here the minimum number is kind of obvious. You can take only one vertex and say that this is our independent set. So here the question comes that what is the maximum number of vertices we can take? Maximum number of vertices to form an independent set. So here this maximum number is what we need to find. So in this example, it's obvious that the maximum number is only one. So we need only one vertex to find a graph. Okay. So there is one question here on the chart.
So in this, if it is a chemical, then we need 4 separate boxes, no, madam, or 4 separate places.
Yeah, ma'am, I shared in the chat that question.
Yeah.
If you can.
So what do you have to do here? Can you brief me the question? The image is not loading.
Okay.
So this is very famous graph. It's known to be Peterson's graph actually. It's some star-shaped graph.
You are not able to copy, ma'am, that from the chat?
No.
Okay.
Actually, so I'm writing in the tab, so it's.
Yeah, that's. Actually, when I solved this problem for the assignment, I got 4. Then the answer was wrong. It came 3. Then I redone the whole thing. Then I finally got 3 as an answer. But I think the only problem is you have to first cover the external periphery vertices and then only go to the internal one. Then you will get the right answer, 3. But if you straight away take one vertex, say for example 1, and then try to go inside the graph, you are getting 4. That's my observation.
Okay.
This is a coloring problem, no?
Yeah, it's coloring, or it can be a minimal set coverage also. It's the same problem. It's the same. You can use different techniques to solve it.
Yeah, 3 is the answer.
Yeah, 3 is the answer, but I got, go ahead, ma'am.
Yeah.
3 is the
Let's
answer.
try to find out what is the maximum independent set here is. Okay, so let's start with, in vertex cover, we have a trick to select that vertex which has maximum degree. Okay, but in independent set, you have to do the opposite of that. So that means try to select those vertices which has minimum degree, because of if they are connected to minimum vertices, we have much what you can say, large number of choices are left there. Okay, so here, but the thing is that each and every vertex is of degree 3. So it's the specialty of Peterson's graph that every vertex will have degree 3. And there are exactly 15 edges, if I'm remember 15 or 10 edges are there. Okay, so let's see. So I think we can start with any vertex because we have to start from something somewhere, right? So suppose I'll start with 1. So if I take an 1 in my independent set, then what are the choices what are those choices which we have to discard? Okay, so if you have taken 1 in your independent set, you cannot take this vertex, you cannot take this vertex, and you cannot take this vertex. That's correct, right?
Yeah.
So you can go with any other vertex. So suppose I'll take the vertex number 9. So 1 I have taken, 9 I have taken. So if you take 9, then 9, after choosing 9, you cannot choose the vertex 7, you cannot choose the vertex 5, right? Because those are the vertices which are adjacent to vertex 9 and 1, right? Because of the same reason, adjacent to vertex. Now there are 3 choices are left. You can select 3, 4, and 6. Okay. So, but here the thing is, if you select 4, then you cannot select 3 and 6 both, right? So here you have to take care that select that vertex by which we are able to create a maximum independence, right? So if you select 4, you cannot select 3 and 6. But if you select 3, you cannot select only 4. So the choice of 6 will still be there, right? So the choice of 6 will be there. So that's why we can say that, okay, I select 3 in place of 4, and then I can select 6 as well, right? So here we can consider a vertex independent set to be of length 4. So that means we can take 4 vertices to create an independent set. Okay.
My
So
answer is wrong.
for coloring,
Minimum is 3.
Independent set. So you have to
no,
create
for coloring,
3
Taken the
between 6
minimum.
only you can create. 3 is
coloring,
storage.
Minimum is 3, maximum is 4.
yeah, maximum is 4. So I'm talking about maximum independent set.
Okay.
Okay. Not a minimum vertex cover. I think for minimum vertex cover, we need 3 vertices, right? Some outer vertices we can take. Okay, vertex cover, I don't know. But maximum independent set is we can consider 4 vertices. Okay, so this is maximum independence.
So in the independent set, always it will be maximum, right? There's
Yeah,
no
in
minimum.
independent set. No, minimum independent set, for minimum one, you can take single one, right? Any single vertex. That will be your minimum independent set. Okay, so in independent set, we look for maximum independent set one. Okay, so let's take one more example. So suppose I'll give you this example, a similar one. 1, 2, 3, 4, 5, 6. Suppose this is the graph. Now what will be the length of maximal independent set? What do you guys think? What will
So
be the
you
length
have
of maximal
to
independent?
take the
Only one,
anything,
right?
The outer ones.
outer ones.
Outer one. Outer one. Correct. So that means 2, 3, 4, 5, 6. 5 vertices. So here the maximum independent set is of length 5 vertex. Okay. So that's all you have to do for maximum independent set. Look for those vertices which are related to minimum number of edges and then select the correct choices. Okay.
So minimum independent set is always default to 1, right?
Oh yeah, default 1.
That's not going to change anyways.
Yeah, that's not going to change. So that's why we never look for minimum.
Yeah, sure.
Similarly, for maximum vertex cover also, you can take all vertices and say this is my vertex cover. Right? So that's why we always look for minimum vertex cover.
Minimum vertex cover and maximum independent
Maximum independence set.
Maximum independent set, what are the, what do you call, uses we can think of? Like chemical is one thing, similar to that, any other word?
Chemical is not, it's a chemical problem is minimum vertex set, I think, not the maximum index independent.
Minimum vertex cover.
Minimum vertices in chemical problem.
So for independent set, chemical obviously is
Virus
there.
in computer.
Yeah, that's also correct. Viruses in computer you can take, or I mean, there will be some similar examples. So in our lectures, we have taken the groups, right? The dance
Class
groups
project.
and class project. No, the class project example is of matching, I guess. So we have taken some dance group that two dances cannot be
Right. Two
that
dancers
dance group
cannot
will.
be in the same dance.
Yeah. Okay, so there are several examples. You have to figure it out which part is based on which concept. Okay.
That will be our job.
Yeah, that will
But
be your
the
job.
maximum, the maximum independent set when you are talking about 2, 3, 4, 5, 6, here the inward degree is not counted, is it? It's a
Sorry. Yeah.
it's a
Yes.
bidirected graph. The bidirected graph. So here,
Mhm.
how do you consider that as 2, 3, 5, 6 as an independent set?
See, if you consider one, then you cannot take any other vertex, right? So the choice, so selecting one is a bad idea, right?
Sure.
Because if you select one, every other vertex is adjacent. So it's an obvious thing that we will select 6, we will select 5, 4, 3, and 2, right?
Okay.
So those are the nice choices we have to go. Okay, is that fine?
Yeah.
Okay, one more example we have. So let's talk about this graph. What will be the maximum independent set here? What do you guys think?
You start
Ma'am,
with
4,
A because that
4.
is
Ma'am, 4.
Yeah.
A.
Four,
Okay.
C.
four,
3,
Yeah,
ma'am.
you start with A.
A, D,
Four.
and C.
Ma'am,
yeah.
3.
So let's see. Let's see.
ADC max
A, D, C.
Yeah.
maximum is
Obviously, A we have to select because A is related to A has of minimum degree. And after selecting A, if I select B, then I cannot select C and D. So it's better to select C. So suppose you will select C, then you cannot select B and D, so you can take B. So that means 3. Right. 3 is the number of maximum independence.
But this also gives the minimum vertex cover rate, ma'am. Either way, this
Uh,
this gives both
in
the.
this
It
case,
meets both the numbers.
no. Here minimum vertex cover is B
Ah,
and D.
okay. B and okay, B and D. Right. Correct.
Yeah, that's what minimum vertex cover. Okay. Is that fine? Both topics, independent set and vertex cover.
Yes, ma'am.
Now the next topic is graph coloring. So again, what you have to do, we have to color the vertices of the graph, not the edges. We have to color the vertices of the graph with the restriction that we cannot give same color to adjacent vertices. So for example, if there is two vertices U and V connected by a direct edge, then you cannot color both vertices with the same color. Right? You cannot take green for both vertices. So you have to take this particular restriction in mind, and then you have to give colors to each and every vertex of the graph. Okay, and whatever minimum number of color we need to color a graph, that number is important, because obviously maximum number is obvious. We'll give each and every vertex a different color, right? Then also the coloring is valid. So that's why here the minimum number is important to us. So how many so what are the minimum number of colors we required to color a graph? So this is the question we need to answer, right? What is the minimum number of colors we need to color a graph?
Ma'am, this can also equate it to minimum vertex graph, minimum color.
No, actually. So
No?
let's see.
Okay.
Because these topics are independent from each other. So
Right.
so let's color this graph
Okay.
only. Okay. So what are the colors we need? So suppose I'll give one color. So suppose I'll color this vertex B with the red color. Okay. So then I cannot use red color to A, red color to C, red color to D. So I can use red color to the vertex C. That's correct. What I can do, I'll color vertex C and D with green color. This is possible. And we can still use the green color to vertex C. So that means here we need only 2 colors to color the graph. Okay, so here minimum number of color is 2. So yes, it is similar to vertex cover in this example, but it's
Okay.
not generally true.
It's not the same. Okay.
Yeah. So let's take one more example.
Because
So
the
give you-
confusion is a
Mhm.
chemical problem, whether we should use a
Mhm.
color technique or the minimum
Mhm.
vertex coverage is the confusion.
Okay.
Which one gives
So-
gives us the right answer?
Okay, so let's this is the coloring graph now.
Yeah.
So here if you find out the minimum number of colors, so the answer will be 3. So let's see one coloring of this graph. Okay. So I'll start with green color. I'll attach green color to this vertex. I cannot attach green color to these 3 vertices, but I can use green color to this vertex.
Correct.
After using green color, I cannot use green color to these 2 vertices. Right? Green color here I cannot use, here I cannot, here I cannot. but I can use green color to this one. Okay,
Correct.
that's correct. And also I can use green color to this, the vertex I cannot use, but 6 I can use.
Yeah.
Right. So using green color, I can color 4 vertices. Now suppose I'll take red one. So I can do red color here, red color here, red color here too, and red color here too.
No,
Right.
red color, that
But-
cannot happen, no? Because the other one.
Yeah, the other one is the red.
Yeah, yeah.
Right.
So we can take the
use
third.
red color here. This
No.
one also cannot.
That also not possible. So we
Yeah.
should
So
use
that
No,
means we
this is
cannot
not
use.
possible, ma'am.
Yeah,
Ah.
right. We have to use another color. So let's suppose white I have used. So white and white and white.
Yeah. So 3 colors.
So we need 3 colors. Now what about vertex cover? So let's see about vertex cover. What is the minimum vertex cover here? Okay. So here every vertex has degree 3, right? So here you can use this logic also. So each and every vertex is of degree 3. And what are the number of edges are here? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 edges are there?
No,
12, ma'am.
12 edges are there. Miss.
And
Right.
15
That means,
in
okay, let me see.
Madam, you have not used JE.
JE.
So this is 1, 2, 3. Yeah, these in between edges I have left, right? So 11 plus 4 will be 15. These edges I have left. Thank you. So that means there are 15 edges. So there are 15 edges and we need to cover 15 edges and the degree of each vertex is 3, right? So degree of each vertex is 3. So that means if I want to cover 15 edges and degree of each vertex is 3, then obviously we need to take care of those many vertices. So suppose there are vertices which are not sharing the common edge, right? So the answer here for the vertex cover is I think 5. So let's see what are this vertex cover. Because if you take less than 5 vertices and they are not sharing each and every edge, then the multiplication of edges, so that means 4 multiplied by 3 is 12 only. So I think we need at least 5 vertices. Right? So suppose this is vertex 6, 2, 3, 5. One is there, this is connected to this one, this is connected to this one. 7, 8, 9. And there's the 10th vertex, right? So here, suppose I'll take one vertex. Since here each vertex has degree 3, so it is only possible to cover at max 3 vertices with a vertex, right? So if I select 6, I'll cover these 2 edges. Now what will be the next choice? Obviously the outer one. So suppose I'll select 9. 9 can take care of these edges, right? If I select 8, so 8 or 7, whatever you will select, you can. So I have selected 9, I have selected 8. So now I have selected 3 vertices, but still there are so many edges which haven't covered, right? So you have to select, suppose I select 4, right? Then 4 will take care of these edges. Then what are the left edges are there? I'll select 3 only. So 3 will take care of rest of the edges, right? But again, 1 is there. So yeah, 4, 5. So that means we have to select one more edge, one more vertex to cover the graph, right? You can select 1 to cover this edge. Okay, so the meaning is here the coloring is 3, but the minimum vertex cover is more than 3. Obviously, you cannot cover the graph using only 3 vertices. Is that
Ma'am,
clear?
is 2 to 5.
H2 to 5. Yeah, so that's the meaning. So there are edges which haven't covered yet. So you need more than 3 vertices to cover the graph. So obviously this question cannot be solved by vertex cover.
So coloring is the technique.
Coloring is the right concept. Yeah. Okay. Because obviously if the graph is larger, it's a little difficult to find the vertex cover by using only logic, right?
So
Okay,
vertex
how do
cover,
you
ma'am, select one, then you cover the edges. And then select the next one which
Next
covers the
vertex.
next, which is independent of the first one, and then try to cover maximum edges with that vertex, selected vertex.
Correct. That should be your strategy.
Okay.
Okay. How do you, so here degree is what? So degree is the number of edges associated to vertex. So here you can see that there are 3 edges associated to each vertex. So that's why the degree of each vertex is 3. Okay. So now for graph coloring, we have one example. We have only taken one example. So suppose this is another example. Okay. So suppose for this graph, what is the minimum number of colors we need to cover this graph? To color this graph? What is the minimum number of colors? 2, right? One color we can associate to center vertex, and we can use another color to color the outer vertex.
On the outer vertex.
Yes.
Right. So here the 2 is the answer. Now suppose I have some more edges in this graph. So suppose these vertices are also covered. Sorry, these vertices are also connected. Okay, and there is one center vertex A. Now in this case, what do you guys think? What is the minimum number of colors do we need?
1.
No, you have to start and working. We have
So we have to start.
Ma'am,
So let's start with
1.
yes.
I think
So we
3.
can, yeah. So let's see. So one color I need to color the vertex A, and this color I cannot use for any other vertices. So let's take another color. So suppose I have associated green color to vertex D, then I cannot associate green
You
color to
can
E
put
and B.
F as green.
F is green.
The E and B will be.
And third color can be E, B, and C. The remaining
But
3
F
can
and
be
C
different.
also
No,
green.
but yeah, we need
Okay.
we need
C
one more
also is
color.
green.
Totally 4 colors.
No,
4 colors
yeah,
we need.
4 colors. C also green.
This is your fourth color. C, green cannot associate to C,
Okay,
right? Green is
green
here,
cannot.
green is here.
Okay, correct.
So 4. So here the thing is, in the outer one, you have odd number of vertices. So that's why the one vertex will left. For that one, we need one more color. So here the 4 is the answer. Okay. So in place of so you can create,
Sorry,
you
I
can
didn't
consider.
understand.
Yeah. So what I was saying. So here in the outer parenthesis, we have 5 vertices, right? 1, 2, 3, 4, 5. But in place of 5, if we have 6 vertices, for example, let's consider the coloring of this graph. Okay. Now, what is the minimum number of colors we need to color this graph? So let's see. One color obviously for the center vertex, right? This color we cannot use for any other vertex. So what I'll do, I'll select one color to this green. I'll select green color to color this vertex, green color to this vertex, green color to this vertex. That I can do, right? And I'll select one more color to color the remaining vertices. So here we need 3 colors to color this graph. Okay, that's the meaning. That's the point I want to mention. See, here we have 5 vertices, so that is the odd number. So that's why we need 4 colors. But in place of 5 vertices, if we have 6 outer vertices, then we need 3 colors. So which is an even number. Okay. Is that fine? Clear?
Yeah.
Observation, madam. More number of vertices, less number of colors. But when vertices are lesser, you need more colors.
Yeah, so it depends on the graph.
Okay.
Actually. Okay. So these 3 topics are important. Now let's go to BFS and DFS.
There is no any fixed kind of set of template that from where we can find that how it can be calculated.
So yeah, so strategy is you have to you don't use another color until and unless it's a necessity. For example, if I have used the red color to the center vertex, now I cannot use red color anymore. So don't use another color until and unless you reach certain point. You reach at this point. That here it is actually not possible to use red color for any other vertex, right? Then only you have to choose another color. Okay.
One strategy is actually you should color all the. Once you choose one color, you complete the entire graph with that color wherever possible.
Yeah,
then choose the
correct.
second.
Then choose the second.
Yeah, because we did in different way for that one graph you told, no, that 10 vertices and 15 edges. There we just took one color, then the next color I chose, and outer edges we colored all alternate colors. And by the time when we came to the inner star, we are using 4 colors. The answer is only 3
Yeah.
actually.
Yeah. So that's the thing. You don't have to use another color until and unless it's a necessity. Now you cannot first first use that color to color at max vertices. That whatever vertices you can color with that particular color. Okay. Now
So
what is BFS
if
and
we think
yes,
about the
Siddharth.
coloring pattern, I'm sorry,
Sorry.
in terms of coloring style, should we start from the inward to the outer vertices, or it should be outer to inner? Is there any kind of
No. It
models
doesn't matter. It doesn't matter actually. You can select from any vertex, but the thing you have to remember is until and unless you reach at this situation that I cannot use this color anymore, then only you have to go to the next color. Okay.
And you also mentioned about the other situation where it's the odd number and the even number.
Yeah.
So is there any kind of logic there that I can think about? Okay, if the number of edges are there, it will be the color.
No. It's this is only for these type of graphs which have one center and some outer vertices in this type of settings only. It's not the case with each and every graph. So we don't have actually formula. So this is only for these vertices, this type of graph with one center and outer vertices.
The only formula is keep coloring.
Yeah, keep coloring. That's
No
all.
guesswork.
Yeah, actually no guesswork because in graph theory also you don't have a closed form for so many things. We just have to go with the logics only. Okay. So let's go to BFS and DFS processes. Yes, is
I
there
think
any
also
doubt?
this I think this problem is also an NP hard problem. Like people in computer science and theoretical computer science and mathematics haven't been able to come up with a nice
Come up with a
algorithm for
closed
this.
formula.
Yeah. So
So
this
for
is still an
coloring,
open problem.
actually, so for coloring, there is one guesses they have made. So they have relate this coloring with the topic polynomial. Okay, that much we have
Yes.
done in graph theory. But further, after how to analyze that polynomial and how to do other things, it's actually very tough.
But
Okay,
this
so for us,
polynomial that comes out, that is even a dangerous thing. Like it's 2 to the power n minus
so
2 is super tricky to be
So
it.
it depends on number of vertices. So that will be the degree of polynomial, and after that, we have to convert this polynomial into some other form. And then we can guess. It's a tough thing to understand. Let's go to BFS and DFS process. Okay. So what are these two processes or strategies? So these are the strategies to answer the question of reachability. So that means, is it possible to reach from one vertex to another vertex considering a path? Okay. So these two processes actually answer that. And how it works? So BFS work in a very systematic way, right? So what we have to do, we'll select one source vertex. We'll explore the neighbor of that source vertex first, right? And after exploring the neighbors, we'll explore the neighbors of these vertices. Okay. So in this way, BFS actually works. So that means step by step. First step is the neighbors of source vertex. The second step is the neighbors of source vertex, and so on. So this is the strategy of BFS process. Meanwhile, the DFS process works in a random pattern. So random pattern means you can first you are at the source vertex. From the source vertex, you can go to any of the neighbor of the source vertex. From that neighbor, you can go to any neighbor of the neighbor of this vertex. Okay, so that means here you have choices. You can select any neighbor and you can continue in that particular direction until and unless you reach at a dead end. Dead end means after this point, there is no new neighbors are there. There is no new or there is no unvisited vertices are there. Then what you have to do, you have to backtrack to up to that vertex which have some new possibilities. Okay, so this is our DFS process. So this is the short explanation of BFS and DFS. In detail, we have so many things. So in BFS, we have levels. In DFS, we have DFS numbering and all those things. But let's consider one small example of BFS and DFS tree. Okay, what is BFS and DFS tree? So we have a graph. We'll apply a BFS or DFS scan on that particular graph, and we'll extract a tree. And how we'll extract a tree? We'll consider those edges which we have used in the BFS or DFS process. Okay, so let me consider one example. So suppose I'll take this particular graph. Eight is there, then 10 is there, 7 is there. Oh, okay. So suppose this is one random graph I have taken. Okay. So here you can consider your source vertex to any vertex. So for time being, let's select 3 is our source vertex. And I am applying BFS scan here. Okay. So what will be the next step? Which vertices should I visit? So I
Zero.
have written 6, 6 twice.
7, 0, 12.
Zero.
Go for 0.
So this is 0. Okay. So 3 to 0, 0. And the next choice will be, what are the neighbors of vertex 3?
Six.
Neighbors of vertex 3 is 0, 7, 12, and 6. So 0, then 6, then 7, and then 12.
12.
Here you can shuffle these vertices. So it's not necessary to explore first 0 or explore first 12. But it's our general convention that we'll explore the least number first. That's all. Okay. But you can shuffle. It's up to you. Okay, now what will be the next step? Explore the neighbors of 0. So what are the neighbors of 0? The neighbors of 0 are 7 and 6 and 8. But 7 and 6 are already been visited. So from 0 we'll go to 8. Okay. Now what is the next vertex? The vertex is 6. What are the neighbors of 6? The neighbors of 6 is 0, 3 and 13. 0 and 3 are already been visited. So we'll go to vertex number 13. Similarly, for 7 also. So what is the neighbor of 7? Neighbor of 7 is 11 only.
0,
So
3,
we'll go to
1.
11. Yeah, 0, 3, 1, 0, 3, 11 is there. So we'll go to 11 because 3 and 0 is already been visited.
Covered.
And there is no new neighbor of 12. So the neighbor of 12 is 11, 3 and 13. And these all vertices are already being explored. Okay. So now let's go to the neighbors of neighbors. So that means let's go to the vertex 8 because there is one unvisited vertex still. Okay. So that's why we'll keep on exploring these vertices until unless we reach at that point where we cannot find any new vertex. But here there is one new vertex, which is the vertex number 10, and which is a neighbor of vertex 8. Okay. So here, whatever this tree is, whatever this tree we got, this is our BFS tree. Okay. Is that fine?
Yes,
So here you can write down the order of BFS2. So that means what is the order which we have used in to find a BFS tree, right? So first I start with 3. Right? So I have started with 3, and after 3 I have gone to 0, 6, 7, 12, and after this one I have gone to 8, 13, 11, after
and
that and 10. Okay, so this is the order of vertices by which we have explored our BFS scan. Okay, so this order is also important. So if the order is given, you can find out your BFS scan and you can answer the questions too. Okay, so this order is our required order which we can use to apply a BFS scan. Okay, is that clear? Any doubt in BFS?
Ma'am,
No,
in the
Is it
question, in the
13,
exam,
11, and 10, is it?
Just one. Sridhar.
It is 13, 11, and 10, right? The last one?
Yeah, 13, 11, and 10. That's 12, 8, 7, 6, 8. Yeah. Yes, Trilok, someone is there. No?
yeah, so in the exam point of view, will they give the graph or will they give the sequence and ask a question? How is it?
No, they will give the graph and then they will ask about the sequence.
Oh, sequence.
Because
Okay.
in the sequence, from sequence, it's actually tough to go for the graph.
Yeah,
Right.
okay.
Okay. So from
But I
graph
think
to
this,
sequence, they will ask.
and the in the instruction videos, the way they have explained the long shot, I think this is much more, the one you should just explain the technique of putting a graph.
Yeah.
This also gives the level also. Actually, if you can
Yeah,
find what
correct.
is the level against each, okay.
Right.
This
So
is,
here, these vertices will be of level
yeah,
1.
yeah,
These
you can
vertices
easily
will be
find
of
the maximum, minimum level and all those things you can find.
right.
But in
Everything
the
will
video,
find.
in the video, the technique what they explained was more lengthier and more complicated. If I go, it will take a lot of time.
Yeah, but that technique also we need because if you want to use some program and all, you need steps, right? To come
Okay.
to apply, right?
Sure.
So this is the brief idea of BFS and DFS.
Yeah.
Sorry, BFS. Now let's go to DFS. Okay, so in DFS, what you have to do, you have to go in random order. Random order means there are several choices we have. We just have to choose. We have to go in one direction until and unless we reach at a dead end. Dead end means there is no new vertex to visit. Okay, so let's start a DFS scan here. So again, I'll start with 3. So for 3, what are the choices I have? I can select vertex 7, vertex 0, vertex 6, and vertex 12. So among these 4 vertices, you can select any of the vertex. Okay. So what is the vertex you want me to select?
Say maybe 0.
Okay. So let's see. Let's stick with our convention. We will select the minimum one. Okay. So from 0, where I can go? So from 0, I can go to 7. I can go to 6. I can go to 8. So from 0, let's go to 6. So from 6, I can go to 3, but 3 is already been visited. 0 is already been visited. So 13.
13.
Right. So from 13, we can go to 12. From 12, we can go to 11. Right. From 11, we can go to back to 7. So now from 7, we reach at a dead end. From 7, the neighbors of 7 are 11, 3, and 0. And all are already been visited, right? 0
Right.
is there, 13 is there. Yeah, sorry. 0 is
0,
there,
3
3
and
is
11.
already there, and 11 is already there. Right. So we have to backtrack. So let's go to 11 back. So as you reach to 11, there is also no other choices. Right. So let's go to 12 back. So from 12 also there is no other choice. Let's go to 13. There is no new vertex, right? Let's go to 6. There is no new vertex. You have to get back to 0 only. So at 0, there is one new choice, which is the vertex 8. Right. So we can go to 8, and then from 8, we can go to 10. Right. So this is the one type of DFS tree. That's how we can compute DFS. Okay, so now here also you can order the vertices. That means you can write an order of vertices in which you have scanned your DFS, right? So first we have started with 3, then go to 0, then go to 6, then go to 13, then go to 12, then go to 11, then go to 7, and after 7 we have visited 8, and after 8 we have visited 10. Okay, so this is the order of visited vertices. Is that okay? Clear? Any doubt?
No, ma'am.
Okay.
Excuse me, ma'am.
Yes.
Ma'am, why did you take only 0? You told that you can take only 0, the 3, 11, and 13 as the source. Why can't we take 8 as the
No,
source?
it's okay. You can take any vertex as your source. So they will generally mention the source vertex in the question.
Okay.
Okay.
And
So it is
this
possible to, yeah.
the method which you taught for DFS and BFS,
Hmm.
it can be used for most of the questions which would be given in the end term, no ma'am.
Yeah, that's correct. Because these are the short questions. You don't have to go by the long process. You can just consider the tree or consider how you will scan a BFS, how you'll apply a BFS scan on that graph. So you can use these two methods too. Because they are same. I just abbreviately explain them. I haven't write down the columns true, false, visited, not visited, Q and all. I just briefly explain what we are actually doing in the process. Is that okay?
Yes, ma'am. Thank you, ma'am.
Ma'am, and if there's a question saying what is the shortest path we should use BFS and which is the longest path we should use DFS. Is that correct? My understanding in the exam.
Yeah, for shortest path we have to use BFS, but for longest path we don't have to consider DFS. Okay, so DFS is not for longest or shortest path both. Only BFS process, BFS can be used for finding shortest path.
Okay. And longest path, normally they don't ask that question, I think.
Yeah, because we don't need longest path. For longest path, we can go round and round. But there is
Okay.
one longest path which is related to topological sorting. So that is the different concept.
Okay, sure.
But for shortest path, we can use BFS process.
Okay.
Okay. So now we have one problem of finding shortest path in weighted graph. So now we have those graphs in which each and every edge consider a weight. So suppose there is a graph, suppose this simple graph. Right. So in this graph, I have some edges, but if I associate some real number over those edges, those numbers will be the weight of these weight of the each and every edge. For example, I'll associate it 7, -8, 1, and 2. Right. Now this is a weighted graph where the weight are associated over each and every edge. The weight of this edge is 7, the weight of this edge is -8, weight of this edge is 1, and so on. Right. So these are graphs are known to be weighted graph. So in weighted graph, what are the questions we need to answer? So there are two types of question. One is the single source shortest path. And another one is the all pair shortest path. Okay. So what is single source shortest path? Single source shortest path means first you will fix a vertex as your source, and then you will find out all the shortest you will find out the shortest path to each and every other vertex.
We use
For example,
Dijkstra, right? Dijkstra we can use for single.
Yeah, correct. For single source shortest path, we have two algorithm, Dijkstra's algorithm, Wellman-Ford algorithm. And what is all pair shortest path? All pair shortest path means for any pair of vertices, you have to find the shortest path in the graph, right? So it's an all pair shortest path. So they all have their each and their applications. So simple applications of single source shortest path is the distribution centers. For example, you have several places over which you can select your distribution center. So what you'll do, you'll select that place which is in the center, right? So that means the path to any other location is the shortest from that particular place. So for that one, you can use single source shortest path to find such a thing. And for all pay shortest path, you can consider an airline network or any travel networks, right? Because we need the minimum distance between any two cities, Bangalore to Delhi, Delhi to Mumbai, or anything. So here we need all pay shortest path thing. Okay, so now we have actually algorithms to find out single source shortest path and all pair shortest path. One is the discards algorithm. Okay, so discards algorithm is actually used to find out single source shortest path. In here, what is the strategy we use? So the strategy is we start with our source vertex and we think that we have burned that particular vertex and the fire is expanding in each and every direction. Now what we have to do, we have to consider the burning time of each and every source vertex, each and every other vertices as our shortest path. So if some vertex can be reached, okay, so let's take one example. So by example, it will be easier to understand.
Ma'am, this is useful only when there's a weighted
yeah,
edges,
there is a
right?
graph
Not,
with no negative weights.
no, not if you use all single unit graph, then this will not work, right?
Single unit means?
No weighted.
No weighted, it won't work. Yes.
It won't work. Okay.
So this is only for weighted graph and
Weighted
also
graphs.
those weighted graphs with no
Negatives. No negatives. Okay.
No negative edges. Because for a negative edges, it will create problem. So
Yeah,
suppose I have this graph.
No negative edges and with weighted. With weights.
Right. 9, 13, 2, and 6. Okay, so suppose this is the graph and I want to apply discards algorithm to find out the shortest path from the vertex A to every other vertex. So here vertex A is our source vertex. Okay. What I'll do, initially I'll say that, okay, the distance of each and every other vertex is infinity. Okay, so this is the first thing I'll do. Then what I'll do, I'll start a fire from the vertex A. So now the fire is expanding in every direction. So the fire will take 4 minutes to reach vertex B and the fire will take 5 minutes to reach vertex C. So what will be the next vertex which will get burned after the vertex A?
B.
B, right? And the time of burning, the burning time of vertex B is 4. So this 4 is actually the minimum distance from the vertex A to vertex B. Okay. Now suppose the fire reach at B, and what will be the next burning vertex?
C.
C. Next burning vertex will be C. C.
Oh,
because
C, right.
at 5 minutes, C will burn. Right?
Yeah.
So the burning time of vertex 5 will be C. Now the fire actually reached to vertex B and vertex C, and it actually gone 1 minute ahead from vertex C. Okay. Now what will be the next vertex which can burn?
E.
E is the vertex E, because the fire can reach at vertex E at the time 8, right? Because 5 minutes
5
it will
plus
take
3.
to reach at 3, C, and then 3. So 5 plus 3 will be 8. Now at 8 minutes, what is the situation of the fire started from vertex B? So at 8 minutes, fire will go up to some halfway here, right? At 8 minutes, fire will obviously go somewhere halfway here, but it already reached to E. Now it will started expanding over these directions too. Now what will be the next vertex which can burn? Is the vertex D, right? Because fire will reach to vertex D at the time 9 plus 4.
It will come from
right?
B. Yeah.
So it will come from B. So the burning time of vertex D is 13. Now it will start expanding in every. Yeah.
So always you should add the edge value to the previous number and see which is the least one, and then we should consider that. So 9 plus 4 is 13, whereas 8 plus 13 is more than 13, right?
More than 13. Yeah. Right. So that's the only thing you have to do. Similarly, here also if you do 8 plus 6, you will get 14. And here if you do 13 plus 12, you'll get 15. So that means burning time of F is 14, the minimum one. Okay, 8 plus 6. Right. So burning time of vertex F will be 14. So this is our discards algorithm. And here, whatever times we'll get, these are actually the distance from our source vertex A. Is that clear?
Can you repeat the last statement, ma'am? I didn't get that. So what is the
So
question
see,
we are?
So see, at time 13, the fire will start from vertex D. At time 8, fire we have already started from vertex E. That means
Correct.
fire will take 8 plus
8
6,
plus
that
6.
means 14 minutes to reach
Correct.
at vertex F from this path. And
Okay, so
fire will take 13 plus 2, 15 minutes from
so
reaching
the
from
process I
vertex.
understood, but the problem what we are trying to solve is what is the least time which will the fire to take from A to F.
Correct.
So that is the
A to
8
F.
plus 6 is the 16. The 8 plus 6 is 14 is the minimum time it will take from going from A to F. So in a problem in an exam, typically such a graph will be given and asked to find out the minimum
Distance
time,
between
minimum distance and the minimum time it takes from A to D or A to E. They'll
Yeah,
give
A
a
to F.
source. They'll give a source
Right.
and they'll give a destination and say what is the least timing or least distance, and we have to do this process to calculate and give the value. Is that right, ma'am?
Correct.
Okay,
Yes.
thank you.
Ma'am,
Okay. So, yes, Muskan.
ma'am, such type of question will take too much time in exam. So how to approach like in short time?
No, it won't take too much time. See, you just have to consider the minimum numbers. So here 4
Yes.
and 5, what is the minimum 4? Right. So after at reaching 5, you have two things. You can go from this path, which will take 5 minutes, or you can go from A to B and then B to C. It will take more time, right? So you have to select the smaller path, which is 5. So it won't take much time. So it will just need a little bit of practice to get a little handy over this process, but it won't take much time. Just do one or two couple of questions. You'll feel that it's easier actually.
But ma'am, we have to check every possible edge, right?
Yeah, but the graph is not that big. So this is the maximum graph for there will be more than one or two edges. So they won't give such a big graph to consider. Only smaller graphs will be there. Okay.
Okay.
Ma'am, one
Because you
question.
know how much time it will take. Yes.
Ma'am, in this case, you deliberately took possibly to explain to us the process A to F. But in the exam, if they say find a minimum path from A to say E, so
Then 8 will be your answer.
I don't have to I don't have to do the complete graph, right? If I
Right,
do
correct.
up to E is sufficient.
Yeah, that's also sufficient.
Okay.
You don't have to go for F and D and all.
If I can reach up to E, if I able to calculate 8, then I don't have to proceed further.
That's true.
Because there's a possibility that in the exam the graph can be much beyond E and it can go 4 or 5 steps into the right.
Oh, there is a possibility of smaller path from F to E also. In that case, you have to consider that one also. There is a chance. If you come by A, B, D, F, E, then you
they will also give you the source of it. So
Yeah, as long as you can cover all the edges of E, then you don't have to complete the graph. That's my understanding.
that's good. Okay. So now there is one more algorithm. So here we precisely mentioned that we won't use Descartes' algorithm if we have negative edges. But what if we have negative edges? Then how can we compute the shortest path? So for that we'll use Bellman-Ford algorithm. Okay. So we have done Bellman-Ford algorithm in detail in the previous session. So if you want to recall it, you can go to the summary session of week 11 or week 10 or week 11 and you can find it there. But from exam point of view, it's not that important. That's why I'm skipping this topic. Okay. But the only thing you need to understand for Bellman-Ford algorithm is, first thing is, it is used for finding shortest path with the source, right? That is single source shortest path. And the second thing is,
with positive and negative both edges.
yeah, that means with positive and negative both edges.
But it can't be a negative cycle.
That's also correct. So that means here, then this point is applicable to every situation, every algorithm. If there is a negative cycle, then you cannot apply any algorithm to find the answer of shortest path because the shortest path problem is not defined for negative cycles. Okay, so this is one red remark you can say. So if there is a negative cycle, then the problem is not defined because this negative path, the shortest path problem is actually not defined if we have a negative cycle. So that means we cannot use we can't use any algorithm, not only Descartes, Bellman-Ford or flawed washer, any algorithm is not applicable in this particular case.
Ma'am, what about zero cycle?
No, zero cycle will work. Zero cycle will work to us because it won't decrease the length of the path. Okay. But the negative cycle will decrease the length of the path if you revolve around the cycle. Right? So zero cycle will work, but these negative cycle won't work. Okay, is that fine? Hello, am I audible?
Yes, ma'am.
Yeah.
Yes,
So
ma'am,
the
clear.
next point is we have to find out this minimal cost spanning tree. Okay. So what is a spanning tree? Spanning tree means suppose we have some graph. Then from this graph we have to extract a tree which will take care of all the vertices. Okay. So suppose you have this graph. Then what you have to do? You have to find a tree which will take care of all the vertices. So that means you have to select vertices and those edges which are not creating a cycle and connecting each and every vertex. Okay. So one possible spanning tree is you can select these vertices. Right. So this is your one possible spanning tree. But this is in case of unweighted graph. So suppose I have some weights over here, then you can actually talk about the weight of this tree. Right. So what is the weight of tree? You have to add all the weights of each and every edge, and that will be your weight of tree. So the question is we have to find out what is the minimum cost of spanning tree. Okay, so what is the cost of minimum spanning tree? So for that, actually, we have two algorithms. One is our Prim's algorithm and another one is our Pushkal's algorithm. Right? So we can use any one of them to answer this question. Okay, so I'll take one example to discuss these algorithms. So this is our graph. Okay, so this is the tree. Sorry, this is the graph, weighted graph, and here we have to find out what is the minimal cost of spanning tree. 6, 5. I think I have taken similar example in the lectures too, but you can consider the concept from this one only. Okay, so this is our graph, and here we need to find out what is the minimal cost spanning tree is. Okay, so I'll discuss first of all Prim's algorithm. So the process of these two algorithms are actually a little different. So in Prim's algorithm, what you have to do, first you have to select the root of the tree and then you have to grow the tree. So for growing the tree means what? You have to select the branches of tree. What are the edges we have to select as a branches? So we have to consider two conditions. First is it should not create a cycle, and second one, it should be of minimum cost, because ultimately our purpose is to find the minimal cost of spanning tree. Okay. So Prim's algorithm says first of all scan the graph and find the edge of minimum cost, so very minimum cost. Okay, the least minimum cost edge. So here, what is the least minimum cost as you're observing?
A to C.
Are you sure?
B to C.
B to E. Sorry, this is E.
B to E.
B to E. Yes.
C to E, ma'am.
So Prim's algorithm says take this edge as your root. Okay, and now grow the tree. Grow the tree means you have to attach some edges. So what are the edges? So for now you have to select the choices. So I can attach this edge because B is there, right? So you can attach only those edges which has one endpoint in our tree and another endpoint is outside the tree. Okay, so this edge you can associate as the branch. This edge you can associate this one, and this one. But again, the thing is we need to consider is it should not create a cycle and it is of minimum cost. What will be the next edge I should consider?
E to F.
E to F, ma'am. E to F.
E, B, C. This is of cost 4.
EF is 3
Ma'am,
only.
E
B,
to
C.
F.
E to F is 3.
Oh, sorry, yeah, right. E to F is of 3.
E to F.
Correct.
Ma'am, in this type of problem, the source is not given, right?
No. Source is not given.
Not given. You have to take a minimum of the given weightage.
Right.
And if there are
Okay,
two
so
branches are having same number, same weightage,
then you have choices. You can choose any one of them.
Fine.
Right. So here the next step will be to select the branch B to C. Right. Now the next step will be to select the branch C to A. Right. because and now the next step will be select the branch F to G.
Yes.
Okay, now we have left with the vertex D.
To
So
D.
we can select C to D of cost 5. Right? Because to reaching D, there are 4 edges and 3 of them is of cost 6. So we have to select minimum, which is 5. Okay. So this is our minimal cost spanning tree, and the cost of this tree is sum of the cost of each and every edge. So here the sum is 3 plus 4 plus 5 plus 3 plus 4 plus 2. Right? So this will become 10 and this will become 11. So 21 will be the cost. 21 will be your answer as the cost of minimum cost spanning tree. Is that okay? Prim's algorithm, any doubt? So Prim's algorithm, I have to select the choices. Yes.
Madam, from D to F, why there is no connection?
But we don't need a connection D to F. So if you want to reach from D to F, you can use this path. Go to C, go to B, go to E, then E to F. Right? So it is ultimately connected. Connected means we need a path, not the direct edges.
Okay, okay. But also it should have all the vertices.
Right. Right.
Okay. Got it.
Okay. So this is Prim's algorithm. But Kushkal's algorithm is, I think, kind of easier because what you have to do in Kushkal's algorithm, you first of all, you will consider each and every vertex as your disconnected components. Right. So first write down every vertices, and now you have to plug in the edges in such a way that these edges will be of minimum cost and they won't create a cycle. So Kushkal's algorithm is a little easy than Prim's algorithm because in Prim's algorithm you have to consider the choices and then proceed. But in Kushkal's algorithm, you just have to consider each and every vertex as your disconnected components and then attach the edges to connect them. Okay, but attach the edges in such a way that it won't create a cycle and it is of minimum cost. These 2 points you should always remember that we don't have to create we don't want to create a cycle, and the cost of each is whatever we are considering should be of minimum cost. Okay, is that fine? Now here, can you guys guide me what are the edges I should consider? First edge will be
BE.
BE, correct?
And we can
A to
take
C.
EF or
E to F.
SC.
E to F.
E to F.
SC.
E to C. Yes.
We can take
Next one.
C to B, CB.
B to C,
B to C.
F to G,
B to C.
FG.
F to G.
Then G. F to G.
And then C to D. C to D.
Correct. So ultimately, we'll get 21 only. And in this example, we are getting the same tree, but it is not necessary to get the same tree using both of these algorithms. Okay, fine. Clear? Any doubts?
It's not necessary that you
No, ma'am.
Sorry, Naren, your voice is breaking.
Even in Prims, we can get a different type of a tree if the edge weights are different. In the sense,
Right.
you have the same 4 and 4 are there, where from B itself you have here, for example, 2, 5, 4, 6 are there. But if there are instead of 6, if it was 4, then we would have got a different tree.
Right. So it depends on the edges and how the graph is looking. Okay.
I'm
So
sorry.
these two algorithms are actually easy to apply, and we can find it the graph cost of annual cost time. Yes.
Ma'am,
Yes,
ma'am,
please.
what is the basic difference between both? Because we are taking the minimum edges and joining them.
Yeah, but in Prim's algorithm, we have a choices to take, right? We cannot take every edges. There are choices, and the choices are we have to grow our graph, grow our tree. So our growing tree, we have to consider the branches. So that means, see, in Prim's algorithm, once I have selected the root, I have few choices only. So this is B to E I have selected. Then you can consider, you can attach this edge, this edge, this edge, this edge.
That means
This
connected
edge,
edges,
these.
right?
Yeah, only connected edges you can apply.
In
But
Kruskal,
in
we can
Kushkal's algorithm, we
randomly
have
any edge.
independent choice. Right,
Okay.
randomly any edges. Okay, so this is the basic difference. Fine. Okay, so that's all.
Is it
on my
guarantee?
side.
Excuse me, ma'am.
Wait.
Madam.
Yes, Amrin.
It gives it is guaranteed that whether we use Kruskal or Prism, it will always give the same cost. If
Yes.
graph is same.
Because that's correct.
Okay.
Cost will be same, tree may differ.
Yeah, image may be differ. Minimum cost path, whatever it will be created, may be different, but the cost will be always same.
Yes, the cost will be always same.
Okay.
Okay. Yeah. Any other doubt? Any other doubt from any other topic? Because that's all I have from my side. I'll take your doubts now. You guys
Can you explain an
Ma'am,
example we
take the
get
example of
cycle?
Negative cycle example. Yeah, we can
No.
take a negative cycle example. So suppose this is A to B, then B to C, and here I will create a negative cycle. C, D, sorry, my font handwriting. D, E, F, G to connect it to B. Okay, so suppose this is some 2 to 3, and here I have 1, -1, -2, and 1. Okay, now what is the cost of this particular cycle? The cost of this particular cycle is 1 -1 -2 plus 1. Right? That means -1. And here, if you go around this cycle, so that means the cost, you can reach from A to C via this path, A to B to C, right? The cost of this path will be 5, right? But if you revolve around the cycle once, the cost will change. If you revolve 1, then the cost will be 5 - 1, which is 4. Right? So that's why here there is no specific numbers, no specific minimum number we'll get if we have a negative cycle. Is that okay?
So in both of these algorithms, negative cannot be taken, right? No?
Yes, negative cannot be taken at all.
Ma'am, will we
In-
write answer 5 or there will be no answer for this?
Yeah, there won't be no answer for this one because the problem is not well defined. There is no smallest number or shortest number we can consider as a shortest path length, right? And
Ma'am,
every step,
question
how many times? Yes, Neetu, sorry.
Ma'am, question number 3, graded assignment
Question
9.
number 3 from graded assignment.
9.
So there is one wording problem here. So which of the curve in the following figure enclosed the negative area on x-axis in the closed interval? That's your question, right?
Yes, ma'am.
So here the answer is 2 and 3, but the thing is they have 2 and 4 is the answer. So enclosed under.
Ma'am,
Yeah,
please
I'll
show
take-
the question. Show
Yeah,
the
I'll
question.
share my screen here. So see, this is the question, right?
Yes, ma'am.
So in the figure 1, what is the question? Which of the
Ma'am,
curve?
ma'am, I have to ask why option 1 is incorrect.
Yeah, so actually enclosed a negative area on x-axis means sum of the areas. So here this area will be bigger than this area. So if you sum, you'll get a positive answer. Are you
The
getting my
answer
point?
should be 2 and 4, right?
Yes, ma'am.
Yeah, the
2
answer
and
should be
4
2
will
and
be
4,
answer,
but
na
the
ma'am?
wording is little confusing in this question. They should have clearly mentioned what is the total area. The total area will be negative. So they just have mentioned enclosed the negative area. So that's why you might confuse with option 1. But here
Yes,
enclosed
ma'am.
with negative area means total area. So here you will get some positive bigger quantity plus with a smaller negative quantity. So ultimately you will get a bigger positive area. Okay, that's there.
Yes, ma'am.
Yeah, they should have mentioned.
No, madam.
Ma'am,
With this wording, it encloses a negative area. Only the all three except C, all three will be enclosing a negative area. No, madam. Not like that.
Yeah. So I mean they are meaning enclose the negative area means if there is a smaller portion that is enclosed, then also we can think that the option 1 is correct. But they are
Right.
saying that total area should not be negative, something like that. So wording is confusing. We have
Yeah,
discussed this question in the session also, I guess. Same
Ma'am,
question.
I have one question from mock test.
Yeah, so we have separate session for that. So we'll take that question.
No, ma'am,
after
I
this.
have to ask one question from mock.
Yeah, so can you share me the screenshot because I actually don't have mock right now.
Ma'am, I can't because I'm not able to share.
So can you just brief me the question?
Ma'am,
Which question
two
I can
options.
share it?
I think it is first question and two options are same for the question.
Madam,
Okay,
can
two
you tell
options are
me
same.
the question number or which mock? I will share it.
Let me see if I have. Okay, so is this the question? A firework is projected? No, they have different options. 15. Yeah. So question 2 has the same options. No, the question 2 also have the different option. Which question you are telling? Hello?
I think he's talking about the very first question.
Oh, mock for end-term release.
Yeah, he's
Yeah.
talking about the very first question. The NAT
Very
type.
first question.
Yeah, choose the
The
most relevant
firework
output.
question.
Ma'am, question number 3.
Question if both of the tasks are performed at this question.
In
Just
total,
Actually,
how many assignments did Rahul pass? That one, no, ma'am?
I actually don't know. Actually, I have
I
the
think
old
questions are
mock.
shuffled.
Ma'am,
Questions are
question number 3 from
Yeah,
from quiz
question
2, mock quiz 2. Question number 3, ma'am. Sir, ma'am, different curves and functions and
actually I
You are
don't
not
have a
able to
mock.
share. I can share it. If you can tell me which mock and which question, I will share it.
Yes,
Quiz
Neeru,
2
just tell.
End-term mock, I think.
time.
There is
No, she's talking about Mark 2. Mark 2.
Let her talk.
1%
Let
talk.
her tell. Yeah. Needu, just talk. Just tell the question.
Ma'am, quiz 2, timed mock quiz 2. Ma'am, only one mock was there for quiz 2.
Yeah. 1 second. Okay.
Question
Quiz
number
2 timed mock I opened. And which question number?
Question number 3.
Question number 3. Madam, I will paste it, madam.
Mm-hmm. Two options of same answer. Like this could be a printing mistake. Don't worry about that much. Because it can happen in mock. Mock are not graded, right?
But it is considered as wrong, and it was graded
Okay.
mock. Yes.
Mm-hmm. Yes, Naren, just
Yeah,
share me
1
the
second,
screen.
madam. I'm just selecting from my screenshots. This is the question and one more. Yeah, mine also it is wrong only.
Wait a minute. Sameksha, I want to ask something. Like, will there be a official mail regarding the syllabus for math?
No, we'll discuss syllabus in the next session. I'll told Samriddha to discuss.
Okay. Sorry, and which session is that? Yeah, maybe I don't want to miss that part. So which session you're talking about?
Yeah, so in the next revision session, I'll tell Samriddha to ask
Okay, that's on
to explain the weightage.
On Thursday.
Session.
Madam, I have posted, madam.
I haven't received. Let's wait for a minute. So you have sent to me, right?
I sent. I did not press that blue arrow mark. I just.
Yeah, I just got it. So here, what's your doubt? Let me see. Also, actually not able to download.
Ma'am, two options are same, and I have marked both of them, and answer is considered as incorrect.
Which two options are same?
Ma'am,
Option
second
2 and 4.
2 and
so
5th.
option.
Ma'am, 2 and
2 and 5, yeah.
So 2 says 2, C and 4, right? So
Yes,
let me go to 2. So
Fifth
2
is
is a
also
exponential function, and C says line through 0,1. So consider function lines through point. C. What does this means? Function in column A lines through the point 0,1 in column B and plot in column C. Okay, so if you substitute 0 over here, you will get e to the power 0 is 1, 1 plus 1 by 2. So this is correct. 2 to C is correct. And then the graph of this function, it's a exponential function, right? So this is sine function, right? So 2 to C2, what is the next one? 2 to C2 4.
Yeah, and
This
even
is not a
fifth option.
parabola. So yeah, but by the line only we can say, yeah. So y is equals to one line is only in 4. So yes, this is correct option.
Yeah, fifth option also says 2 to C to 4,
This is also correct. Both options are correct.
but it is
So
given wrong.
there's just a misprint only.
How
Okay,
it
I'll
will
ask
be
them to
affecting
remove.
our grading?
That thing I actually don't know. Mock, is it they are giving some extra marks or something like that?
Yeah, bonus
Yes, ma'am.
marks they are giving.
Okay, so that's why you are saying it is affecting. Yeah, I'll correct this mistake. I'll tell them to correct it. Well, that option is correct.
Okay, ma'am.
Okay. Any other doubt? Any other thing?
No, ma'am.
Okay, so thank you guys for joining.
Ma'am, sorry, ma'am. I'm posting one question. 1 second.
Can we discuss it tomorrow because I have some other
Oh,
session?
okay, no problem. No problem. Great.
Yeah, we can discuss in the next session.
Sure.
Tomorrow's our session is there? At what time?
There is another session. Yeah. So we have Thursday.
Okay.
From 8 to 10.
Okay.
Samriddha, I'll take that session, so you can ask whatever the left or the outside.
Most of the
Thanks for the
syllabus
session.
is from
6.
8 to 9 to 12,
8 to
right?
11. Yeah. Most of the you can consider from 7 to 11. Limit, you can consider
Okay.
limit, continuity, differentiability, and then graph theory.
Okay.
7 to 11.
Yeah.
Oh, thank you.
When you will be giving the split up of marks, madam, like
Tomorrow, in the next session only. So I'll ask Samriddha to get it from the sir.
okay, madam. Thank you.
Great.
Thank you for the session, madam. Good night.
Thank you, Jay guys.
Thank you.
Good night.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.